This is our third video on acid-base chemistry, and here I'm going to talk about buffers. So first of all, what is a buffer? A buffer is a solution that is able to resist changes in pH when small amounts of acid or base are added, right? So an acidic buffer might contain a weak acid and the conjugate base of the acid. So for example, acetic acid and sodium acetate. Whereas a basic buffer would contain a weak base and the conjugate acid of the base. So for example, you could make a basic buffer out of ammonia and ammonium chloride. So how does a buffer work? How is a buffer able to resist changes in pH? It works by interconverting between the two components. So remember, again, you have two things in that buffer: the acid and the conjugate base, or the base and the conjugate acid. So when you add acid or base, you interconvert between the two forms. So let's say we have a buffer that's composed of a mixture of acetic acid and sodium acetate. Okay? When you add sodium hydroxide to that buffer, what happens? The sodium hydroxide reacts with the acetic acid and converts it into additional sodium acetate. So basically you convert acetic acid into sodium acetate. Or if you add HCl, then the HCl reacts with the basic component of the buffer. It reacts with the sodium acetate and converts it into acetic acid. Okay, so you either wind up converting acid into conjugate base or conjugate base into acid. Adding acid or base converts between the two components. Whereas, let's say if you dump HCl or NaOH in pure water, you'll change the pH dramatically. Here, not so much, because you're converting between the two forms. So, how would you calculate the pH of a buffer? So let's calculate the pH of a buffer that's composed of tenthemolar acetic acid and tenthemolar sodium acetate. So let's start out by writing our reaction. Okay, if we had acetic acid, just pure acetic acid by itself, it reacts with water to produce acetate plus hydronium. So how would we write the K for this? Concentration of acetate divided by concentration of hydronium divided by concentration of the acid, acetic acid. Okay, so if we were to take that and rearrange it for the concentration of hydronium, which is what we're talking about, calculating the pH, then that's Ka times the ratio of the acid form of the buffer divided by the base form, or acetic acid divided by acetate, right? So we're going to let X represent the extent of dissociation. So this reaction shifts to the right, and these go up by X. Acetate goes up by X, hydronium goes up by X, and acid goes down by X. Okay. Well then, the concentration of acetic acid will be 0.1 minus X. And if we neglect the effect of the dissociation, that will simply be 0.1. Okay. And by similar logic, but our buffer is not just pure acetic acid. It's also acetate, because we have two things in the buffer, right? So the acetate concentration now is 0.1 plus X. Well, if we can neglect the X here, we can neglect it here. 0.1 minus X is, for all practical purposes, equal to 0.1. and 0.1 plus x is, for all practical purposes, equal to 0.1. We can neglect it in both cases. Well, then we plug 0.1 and 0.1 in here, right? Then concentration of hydronium is equal to Ka times 0.1 over 0.1. Okay, in which case you would take the negative log of that, or we'd be taking the negative log of the Ka, which is the negative log of 1.85, negative log of 1.8 to the minus fifth, which is 4.74. So in this case, we could say pH is equal to pKa. Okay, pKa is simply the negative log of the Ka. P always means negative log. So then that's the case here because the concentrations are the same. See, in the buffer, then your hydronium concentration is the K. Your pH is determined by the ratio of these two ions. When they're the same, they cancel each other out, and the pH and the Ka is equal to the acid dissociation constant, or pH is pKa. Okay? Now, let's calculate the buffer. Let's do a similar calculation. Let's calculate the pH of a buffer that's composed of 10th molar acetic acid and 0.5 molar sodium acetate. Now let's think about this real careful. There's always two things in a buffer, an acid and its conjugate base. So that's the acid, or that's the acidic component of the buffer, and this is the base component of the buffer. Right, so here, in the previous example, the two were the same. Now, we've jacked up the base concentration. Base concentration is greater than that of the acid. So, the reason I'm making a big deal out of this, let's think about this. Your answer should come out to be higher than 4.74. 4.74 was when the concentrations of the two were the same. Now we have more of the base form than we do of the acid form. pH is going to be higher. So in other words, we solve it the same way we did before. The concentration of hydronium is Ka times the ratio of the acid form over the base form, or 1.8 to the minus fifth times 0.1 divided by 0.5 comes out to be 3.1 to the minus sixth power. You take the negative log of that, you get 3.6 to the minus 6, take the negative log of that, and you get 5.44. Okay? So the pH is indeed higher than the 4.74, which is what we were predicting, right? We figured there's more of the base component, so the pH is going to be higher. Okay? Now let's flip it around. Let's calculate the pH of a buffer that's composed of 0.5 molar acetic acid and 0.1 molar sodium acetate. Okay, so now we have more of the acid form of the buffer. One more time, right? This is the acid form, acid component of the buffer, and this is the base component of the buffer. Now we have more of the acid component. So we're going to set this up the same way. X represents the shift. So the concentration of the acid form will be 0.5 minus X, which for all practical purposes will be equal to 0.5. And the concentration of the base form will be 0.1 plus X, which for all practical purposes is equal to 0.1. The Ka, or the hydronium concentration is equal to the Ka times the ratio of the ions. So 1.8 to the minus fifth times 0.5 over 0.1 is equal to 9.0 times 10 to the minus fifth. You take the negative log of that and you get 4.04. So now the pH is lower than 4.74. Okay, But I want you to note that the pH was lowered by the same amount that it was raised in the previous example. In other words, 5.44, which was the last example, minus 4.74 is 0.70. And if we take 4.74 minus 4.04, what do we get? 0.70. So here the pH was lowered relative to the case where the two components were the same. Here the pH was lowered by the same amount that it was raised and in the previous example. Okay, so this is kind of the long way to do it, but I wanted to show you this so you know where some of this stuff is coming from. The easier way to do it is with the Henderson-Hasselbalch equation, okay, and that is simply this equation, that the pH is equal to pKa plus the log of the ratio of the anions. So in other words, the anion form or the base form divided by the acid form. Okay, so for example, what's the pH of this buffer? Let's go through these same calculations one more time. So what if we add 10th molar acetic acid and 0.1 molar sodium acetate? Okay, so pH is pKa. Now one more time, here's this pKa again that I mentioned previously. Remember, P means negative log, so pKa is the negative log of the Ka. So negative log of 1.8 to the minus fifth, that's 4.74, plus the log of 0.1 over 0.1. Two concentrations are the same, 0.1 and 0.1. Alright, so anything divided by itself is 1. What's the log of 1? It's 0. Okay, which means this term drops out. So basically 4.74 plus 0, pH comes out to be 4.74. Okay. Now, what if we want the pH of the let's do the second calculation. We add 0.10 molar acetic acid, but 0.50 molar sodium acetate. So now we have more of the base form of the buffer. So 4.74 plus the log of 0.5 over 0.1. There's that 0.7 that we got previously. That's the amount by which it's changed. So that was basically the log of the ratios. So 4.74 plus 0.7 is 5.44. Okay. And then switch it around, and what if you have more of the acid form of the buffer? Suppose this is now 0.1 or 0.5 rather. If this is 0.1, so now it's 4.74 plus the log of 0.1 over 0.5, right? This switched around. So now it's 4.74 minus 0.7, in which case you get 4.04. So this is really the easier way to do it. Now, let's talk about the effectiveness of buffers. Okay, how effective is a buffer at resisting changes in pH? So let's suppose that a 1 liter buffer is 10th molar acetic acid and 10th molar sodium acetate. Because it's 1 liter, that makes the calculation easy because the concentration automatically becomes the number of moles. So let's calculate the pH after the addition of 0.05 moles of HCl. Okay. So what was our initial pH? 4.74. Right? We worked that out in the previous problem. When the concentrations of the two are the same, the pH is equal to pKa. So what happens? What are we adding to this buffer? We're adding HCl. Okay, we're adding 0.05 moles of HCl. So which component is the HCl going to react with, right? One more time, there's two things on the buffer. This is the acid form, and this is the base form. Okay, so we're adding acid. So what's that going to do? That's going to convert base form into acid form. In other words, that's going to convert acetate into acetic acid. Okay, so the base form will go up the base form will go down and the acid form will go up. So after we add this 0.05 moles, okay, how many moles of the acid will we have? The 0.1 that we started with plus the 0.05 is equal to 0.15. Okay, and how many moles of the base form will we have? That will go down by 0.05. So we started with 0.1, we finished with 0.05, so we went down by 0.05, or we finished with 0.05. Okay, so now because we're dealing with a 1 liter solution, the moles is the same as the molarity. So we use the Henderson-Hasselbalch equation. What's the pH? 4.74 plus the log of the ratio of the ions, 0.05 over 0.15. That is 4.74 minus 0.48, or 4.26. So what was our change in pH units? 4.74 minus 0.26 is 0.48. So we changed roughly half a pH unit. All right. Now, what if we had added that to pure water? Okay. What if we had added that to pure water? Then what would our change in pH be? Well, the concentration of hydronium ion would be, with the pH would be negative log of 0.05. Concentration would be 0.05. That would be 1.3. So if it was pure water when we started with, that would have been pH 7. Okay, so from 7 to 1.3, it's a change of 5.7 pH units. Okay, so there's a small change in pH here. Big change in pH here. And remember also that the pH scale is logarithmic. So every time you change one pH unit, it's a tenfold change in the concentration of hydronium or hydroxide. Okay? And I want to leave you with this last idea here about buffers too. Buffers resist changes in pH, yes, but buffers can also be overwhelmed. Buffers can be overwhelmed. So for example, eventually, if we kept adding HCl, obviously we didn't do that here, but if we kept adding HCl, eventually there would be no more acetate for it to react with, and then there would start to become bigger changes in the pH. So buffers can be overwhelmed, but typically then the higher the concentrations of the two forms of the buffer, the greater will be your ability to resist changes in pH. And that's all I'm going to say about buffers.